You know, our sun, it's the heart of our solar system, but it's also got a pretty wild temper. Solar flares, massive eruptions, these things can literally throw plasma across space and wreak havoc on our satellites, our power grids, even astronauts. For decades, trying to predict this solar fury has been one of the biggest challenges in science. But what if? What if we could teach an AI the fundamental laws of physics to give us a clearer forecast? Okay, let's get into it. So all that drama, all that space weather, it really all starts right here, with the sun's magnetic field. It's this chaotic, constantly shifting system that controls everything from sunspots to those massive solar flares. Figuring out how this magnetic energy, or flux, moves across the sun's surface isn't just some academic puzzle. It is absolutely critical for protecting the technology we all depend on. And yeah, that's the million-dollar question, isn't it? Trying to simulate the incredibly complex physics of the sun's surface is just unbelievably hard. You've got these massive plasma flows, the fact that the sun spins at different speeds, all happening at once. It's a puzzle that has pushed our old simulation methods to their absolute breaking point.
To try and solve this puzzle, scientists have a main playbook. It's called Surface Flux Transport Modeling, or SFT. Basically, it's the go-to method for simulating how the sun's magnetic field gets carried across its surface over time. And look, for a long time, it's been the best tool in the toolbox, but it comes with some pretty serious drawbacks.
The way it usually works is by breaking the sun's surface down into a grid, kind of like how a digital photo is made up of pixels. The computer then runs all the physics calculations inside each of those little boxes. But just like a low-res, pixelated image, this whole method means you can lose a ton of important detail. Sure, you can make the pixels smaller for a better picture, but that gets ridiculously expensive, computationally speaking. So this really lays out the trade-offs, right? These grid-based models, they suffer from something called numerical diffusion, which basically just blurs all the details. But even worse, they tend to lose magnetic flux over time. The simulation literally springs a leak and loses energy, which is a huge problem if you're trying to make a long-term forecast. In a perfect world, our model would be razor-sharp, it would conserve every last bit of that magnetic energy, and it would give us the right answer no matter what resolution we used.
Well, this is where things get really interesting. Instead of just trying to patch up the old grid method, researchers came up with a totally new approach. An AI that doesn't even need a grid. It's like it has a fundamental understanding of the physics, allowing it to build a way better model from scratch.
We are talking about something called physics-informed neural networks, or PINNs for short. Now, a regular AI just looks for patterns in data, right? A PINN is different. It has the actual equations of solar physics, the SFT equation, baked right into its learning process. So it's not just making an educated guess, it is physically forced to find solutions that don't violate the fundamental laws of the universe.
So how in the world does this thing work? Well, the network takes in some really basic info: a latitude, a longitude, and a moment in time. It crunches those through its neural layers to come up with a prediction for the magnetic field. But here's the magic part. This thing called a loss function acts like a strict referee. It's constantly checking the AI's answer against three things: the starting conditions, the boundary conditions, and most importantly, the actual physics equation. If the AI's prediction breaks any of those rules, it gets a penalty and is forced to try again.
So, what's so important to get here is this cycle. The AI makes a prediction, the referee checks it against all the physics, it measures how wrong it was, and then it adjusts its own wiring to make a better prediction next time. It does this over and over, thousands of times, until it finally lands on a solution that satisfies the laws of physics everywhere and at all times. It's not just learning from data, it's actually learning the science.
Okay, but a cool new model is just a cool new model until you prove it works, right? So the researchers put this PINN through its paces, running it head-to-head against a very high-accuracy traditional simulation to see how it stacked up.
This quote from the paper really hits the nail on the head. Remember how we talked about those old models losing magnetic flux? Well, the paper found that the PINN model was way better at conserving it. For accuracy, especially when you're trying to predict an entire solar cycle, this is a huge win.
And this graph, wow. This graph tells you everything you need to know. That blue line, that's the error for the traditional model. See how it slopes down? As you give it more resolution, its error gets smaller, which is what you'd expect. But now, look at the red line for the PINN model. It's flat, and it's incredibly low.
Its accuracy is basically the same no matter the resolution, and it's beating even the best-case scenario traditional model.
And here's that same flux problem, but in stark numbers. A low-res traditional model lost a staggering 24% of the magnetic flux. 24%! Even the high-res version lost 3%. But the PINN model? It lost just over 1%. I mean, that is just a night-and-day improvement in holding on to the core physics of the system.
So these are what we call butterfly diagrams. They're basically a map of the sun's magnetic activity over a full 24-year simulation. On the right, that's the PINN solution, which is our super accurate benchmark. And on the left is the traditional model. You can see it's close, but there are definite differences, especially up near the poles. See those boxes? They're highlighting where the timing of the magnetic field reversal is off. It shows the PINN is catching subtle details that other models just can't see.
So, all this technical stuff, this improved accuracy, what does it actually mean for us, back here on Earth? Well, it means we're taking a giant leap closer to having a truly reliable space weather forecast.
And here's the real-world test. The top row shows actual satellite observations of an active region on the sun way back in 1996. Now the middle row, that's the PINN simulation of that exact same region. And you can just see it does an incredible job of tracking how the real magnetic structures moved and evolved. And it did it with less error than the traditional numerical model, which you can see there on the bottom row.
So let's just boil this all down. What's the big takeaway? This AI approach gives us way more accurate models, especially for the sun's polar fields, which, it turns out, are the key to predicting how strong the next solar cycle will be. Because it holds on to magnetic energy so much better, our simulations are just more real. All of this is laying the groundwork for the thing we really need: reliable, long-term forecasts of what the sun is going to do next.
This whole thing just leaves you with a really fascinating question. We're stepping into a new era where AI isn't just a tool for finding patterns. By baking the fundamental laws of nature right into these networks, we're building tools that can, in a real sense, reason about the physical world. And that could change how we do science forever.